In this video lecture, we are going to see about 4-bit full adder, right? 4-bit full adder we are going to see. So what is the work of 4-bit full adder is that it is going to add 4 bits, that's it. Say for example, if A is going to be a value, so A will be having 4 bit, A0, A1, A2, A3. Similarly, B will be having 4 values, B0, B1, B2, B3. So when I put A plus B, so I'll be having A0, B0. Every time if I say it is adder, every time my C0 will be 0. Please remember, every time my C0 initial carry will be 0. This C0, if it is adder, initial carry will be 0. Apart from that, everything is as usual addition what we are going to do. So I'll go with the example. So this is going to be my A value. This is going to be my A value. I have taken 1 0 1 0 as my A value, and B value is going to be B0 B1. This value is your B value. So if I add it, so initial carry is always 0 is given, right? Now 0 plus 1 is 1. So my carry is 0. So I have 1. So my value is 1. Similarly, it is 0 0 as I have this 1, I'll be having 1. So this is one example. Then I'll go for second example. So this initial carry value is given to be 0. Then the value is A value is this and B value is this. I have assumed A value as this and B value as this. So now if I do, what is the value? 0, 1, 0, 1, 0 is going to be 1. Then 0 is the carry. 1, 1 is going to be 0 and the carry is going to be 1 here, right? 1, 1 is going to be 1, 0. 1, 0 plus 0 is 0, 1, 0. So what is it? 1, 0 I have. So if it is going to be 0, 1, 0, it should be 0 here. So it should be 0, right? Yes, it is 0 and 1 is carried over and 3, 1 will be 11. So this is my final addition what I will be having. The same process is being done here also, right? See here, we are performing 3 bits addition. For performing any 3-bit addition, you need a full adder, right? This full adder should have 2 input, 1, 2, 3. So these are all your input, 1, 2, 3. And how many output? Every time adder will have full adder will have 2 output. One is your sum and another one is carry. So these are your 2 output. Clear? So this C1 will be the input to the next. As usual, what we have seen, this carry is going as input for this one. Similarly, this will be the input for this. So this is how the process is going to repeat. Now, I'll say tell you what is carry propagation delay. Carry propagation delay is very important concept because in order, if I have, this is 4-bit. So if I have 16-bit or 32-bit, what will happen? Now let's go to this criteria. So C0 I have initially. So what about C3? C3 value I'll be getting only when the operation of this full adder is completed, this full adder is completed, this full adder is completed. Until that, this full adder will be waiting for this C3. Similarly, if you see it, this full adder will wait for C1, right? This full adder will wait for this 2 full adder to get complete the process. So this carry is propagating. For that propagation, delay is happening. That is nothing but our carry propagation delay. So we will be dealing many things about this carry propagation delay. For this, we will be designing look ahead carry generator, which we will be seeing. So now we can go to the 4-bit adder subtractor, right? Next, I am going to 4-bit adder subtractor. Adder subtractor concept is very simple, where it is similar to that of adder and it is also going to perform the subtraction operation. First, the operation is almost same. The diagram what we saw is same for, the diagram what we saw earlier is a full adder diagram is almost same when compared to this. The only thing addition what we have is this XOR gate, right? That is 1 and this M is 1. When this M is going to be of 0 value, it is going to act as adder. Similarly, if the M is going to be of 1, it is going to act as subtractor, right? Now let's go for M is equal to 0. If M is equal to 0, as I told already, the initial carry will be 0. M is equal to 0, initial carry will be 0. A0, there is no change with respect to A0 when you compare with the previous 4-bit adder. Only change what we have is with respect to our B naught, B value, right? So this B, I'm just going to add it with a XR value. Say for example, my M is equal to 0 now. If M is 0, I'm going to get a B naught here and my M is 0. If M is 0, what is going to be your output? Obviously, as per the XR diagram, if one input is 0, obviously you will be getting the same output. See here, when my M is 0, whatever is A, that is your output. Similarly, when M is equal to 0, A is 1 here, 1 is output. With this concept, look at this diagram, you will understand it clearly. Now M is equal to 0, one of your input is 0, so obviously the output will be B naught. Similarly here, the output will be, one input is 0, similarly the output will be B1. One input is 0, similarly the output will be B1, similar concept. So whatever B naught, the same thing is going to come, which will make it act as a adder. Now let's come to the subtractor operation. When we come to this, M is equal to 1. When we come to this, M will be equal to 1. If M is equal to 1, what will happen? My C naught will be equal to 1. Clear? Yes. My C naught equal to 1. Then what about this B naught? This is first operand, this is second operand. See here, this is first operand, this is second operand. If I have to perform subtraction, I have to take 2's complement. Yes. So for this, I have to make this bar of B naught. That is, if B naught is equal to 1 here, now here B naught should be 0. Similarly, if B naught is 0, it should be 1 here. So what will happen if M is equal to 1, this input will be 1, this input will be 1, this will be 1 and this will be 1. So what will happen? If this is 1, obviously what is going to be B here? The output is going to be, if it is A bar. If it is B, B naught bar. This is B naught, so B naught bar. B1, B1 bar. B2, B2 bar. B3, B3 bar. It is just acting as a NOT of this value. Look here. This is 0, 1, 0, 1. So what I have done, 1, 0, 1, 0. So this has taken NOT. And also we need that adder 1 should be given, added in the 2's complement. For that, I am making my C naught value equal to 1. That is the C naught. So by looking at this, what is happening? It is performing the 2's complement operation perfectly. That is, if M is equal to 0, it is going to act as adder. If M is equal to 1, all the B naught value are going to get knotted, right? Then it is going to add the C naught value is going to be 1. Hence, it is going to perform 2's complement subtraction. So this is the meaning of 4-bit adder subtractor. Now, as I told earlier, now let's go for the concept of carry propagation delay. Now let's go for the carry propagation delay, which is very important. The problem, I already told you, the problem is the delay of this carry. The delay of this carry. So now let's come to this one. So what I am going to do is that this is same full adder what I am going to have. This is same full adder what I am going to have. In this, what I am going to do is that I am just going to name this one. That is A1, everybody know this A1, B1, everybody know this. I am just C1, everybody know this. I am just naming this output as P1, this output as G1. As usual, this is SI, this is CI plus 1. So I have named this as such, SI, GI plus 1. So now what is PI? The PI is going to be, what is PI? The PI is going to be AI plus BI. PI is going to be AI plus BI. So what is this? AI plus BI. So this is your one. Then what is GI? GI is equal to AI into BI. Clear? Right. Then what is SI? SI is equal to PI XOR with CI. Look at this. SI is this. So it is PI, and what is the other input? CI. So this is your SI. Right. Now what is CI plus 1? CI plus 1 is this. What is this? The CI plus 1 is going to have two input. One is your GI and another one is nothing but PI GI. PI GI. So G1. So if this is going to be your G1 to AI into BI. AI or and BI. Clear? SI is nothing but PI and CI. This is what I have written. Clear? Similarly, what is CI plus 1? CI plus 1 is equal to GI plus PI CI. GI plus PI CI. So PI CI. This is what is the basic thing. Whatever I have here, I have written this. Now in this equation, why I am very much involved in CI equation is that because the problem what I have is with respect to carry, so I am addressing the carry problem. So that is why I am taking the Ci plus 1 equation. So in this equation I am putting I is equal to 0. If I is equal to 0, what will happen? Ci 0 plus 1, so it is C1. Gi will be Gi is equal to 0, so G naught. Pi Ci, I is equal to 0, P0 C0. So this is it. Now again I am putting Pi is equal to 1 in the same equation. So 1 plus 1, so see, this is C, this is C. So this is 2 is equal to G1 plus P1 C1. I already know what is this C1 here. So I am substituting this C1 here. So what will happen? C1 is equal to G0 plus P0 C0. So I have substituted whatever value I have. So I have substituted. So now what I have done, I have multiplied this value. So now I have got C2. Similarly, I am substituting I is equal to 2 here. So that I am getting C3 is equal to G2 plus P2 C2. Right, now I know what is C2. So this is C2. I am going to substitute this C2 in this equation and I am going to multiply. So I will be getting G2 plus P2 G1 plus P2 G1 P0 G0, then P2 P1 P0 C0. This is my thing. Similarly, as I am going for 4-bit, I need C4 also. So I am going C4 is equal to G3 plus P3. Substituting this, I am going to get this equation. Everybody clear how I am getting the values of C? So what I am doing is there for making my process is becoming little bit complex, but my delay is getting reduced. This is the concept. I'll go for the diagram of the same. I have drawn same equation here. I have whatever the equation I have derived there, I have brought the same equation. So C0 is equal to G0 plus P0 C0. Look here, C0 is directly going, P0 G0 I am going to give it to an AND gate, and those two are added, So two things are added. So now let's go to C2. C2 will be having G1, so sorry, this is my equation. C2 is equal to G1. Look here, G1 is going directly, right? Then P1 C1. Look here, this is my P1 and this is my C1 as P1, and look here, P1 G0. P1 G0 is this, that is taken here. Then again P1 P0 C0. This is the third one where it will be having P1 P0 C0. Three things are connected. Those three are connected to C2. Similarly, if you look for C3, I am going to have, what are all the value I am going to have? 1, 2, 3, 4. Similarly, 1, 2, 3, 4. This is how I'll be drawing my diagram, logical diagram of my carry look ahead generator. Similarly, I'll be having for C4 also. Clear? So now this block diagram, P2, P1, whatever I have, this setup is taken as a block. This setup is taken as a block and it is being represented here. This is 4-bit carry look ahead generator.